Welcome to this video lesson. On forehand, I have to apologize, I have to stall you a bit because it takes me a sec to draw out the title. That's one bit of the title. There comes the other bit. Its title sounds a bit like a road movie. We gave it a title from Sturm-Liouville, there it comes, to Green. As in every road movie, it's on one hand about the destination reached, but also about the road traveled. Destination reached, that's Green's formalism, a formalism extremely important in many different fields of physics. And it should belong in every toolbox of every physicist. There's the toolbox. There are many different ways this Green's formalism is introduced in very different textbooks. And of course, all these formalisms, in the end, are all the same, so they don't need to be interconnected. This video will also be how these different derivations, different formulations are all connected. There's the road traveled. This video is meant as an introductory video to enable you to read a standard textbook and understand what they're talking about when they're applying Green's formalism. For the more advanced trickery, we refer you to a further video. I hope you enjoy. Okay, what is the problem at hand? We will study here linear differential operators with a maximum derivative order of p. We denote them as L of p. As its most general form, we take where a p is a function of x and the highest derivative order is p, and the lowest derivative order is 0, a0x, a constant, a function. We let this differential operator operate on functions y, which we assume to be sufficiently smooth. Let's leave it at that for the moment. To help you remember, linearity implied. The name of the game is to solve this equation. That means find the function y given a function fx so that if L operates on y, it reproduces fx. In most cases, at least in physics, the maximum order of the differential equation operator is p equals 2, second order differential equations. And we usually write it in its most generic form as such. This sounds like a lot of complicated language for something which was simply called an inhomogeneous differential equation in any undergraduate course. There we learned that if we find one solution of this inhomogeneous differential equation, and if we find the most general solution of the homogeneous differential equation, under the appropriate boundary conditions, we actually can write down the most general solution of this inhomogeneous differential equation. But please do remember, to find this one solution depended many times on luck or complicated trickery. Because we're talking about operators and linear operators, let us first look at the simple situation of a finite dimensional space, linear algebra. And see what we can learn from here. It all starts by introducing an inner product. This inner product actually defines your space. Once we have an inner product, states can be expanded in terms of components with respect to some orthonormal basis. In this language, suddenly our linear operators are turned into matrices. We will use the infinite analogy to this later on. Define an inner product, And for example, a Fourier decomposition is an expansion in terms of components, only this time there are infinitely many. The thing we are primarily interested in is the self-adjoint operator. But let's work our way up to it. Imagine we have an operator M working from vector space V to vector space W. Those two vector spaces don't need to have the same dimension. The dimension of vector space V equals M and the dimension of W equals M. M forms a map from any state in V to another state in W. For all states from V, we assume a complete set of basis vectors V1 to Vn to exist. Similar for all states of W. A complete set of basis vectors W1 to Wn. Now the map M can be represented as a matrix, where all the matrix elements can be found as Give me a sec. Yeah? Here you see this only works if this inner product, denoted by this bracket notation, makes any sense. And again, remember, the inner product is actually what lays down the nature of the spaces we were working in. So far, so good. We even make it ourselves slightly more easy by choosing the dimensions of the spaces V and W of the same order, n. In this case, the corresponding matrix of the operator M turns into a square matrix. Or, in terms of mapping, M represents an isomorphic map operator. Now we're going to introduce the concept of the eigenvalue operator. We introduce the eigenvalues lambda 1 to lambda n as the roots of the characteristic equation. Whereby I represents the identity operator. The letter P is chosen on purpose. P represents a polynomial of order n. There is a fundamental theorem in algebra that states that for such a polynomial equation, we are always able to find n roots, although they are generally complex and not always distinct. There's our point. The next step is to introduce the eigenvectors. For each lambda I, we can introduce an eigenvector v of I, defined by the following equation. It could be that some lambda i's have the same value. In this case, we take the corresponding v of I orthonormal to one another. So far, so good. The next item on our list is the concept of the Hermitian conjugate of the operator M, denoted as M dagger. First, in terms of matrices. Our operator M is represented by an n times n matrix with complex values. Then the Hermitian conjugate of this matrix is defined as the transposed matrix complex conjugated. What again was transposed? That means interchanging rows with columns. So, we can actually read the inner product of a vector u with a vector v as the Hermitian conjugate of u, that is a row vector, times the column vector v. Let's take this as a definition. Now we're going to let go of a specific representation of the basis factors. Now we define the Hermitian conjugate by the following identity. So what needs to happen is that we have to take the dagger of m dagger times u. That is actually u dagger m dagger dagger, and twice the dagger is again u, so that gives me u dagger m. Multiply it by v, and that should be the same as m times v multiplied by u. This. And that indeed holds. So indeed, we can take this as the defining property of the Hermitian conjugate. Now, finally, what means a self-adjoint operator? Those are all operators for which m dagger equals m. Notice how we moved away from a definition based on a particular matrix representation. Actually, we defined it as this has clearly two benefits. No longer a particular orthonormal basis is needed to represent the matrix of the operator in, so that taking its dagger operator means transposing it and taking its complex conjugated, m dagger. And the only thing actually needed is a definition of the inner product. An inner product operates on two vectors, combining them into a scalar. For people who know about tensors, notice how this nicely ties in with the notion of covariance and contravariance. So, two things. Independence of how we represent linear operators, m, on a finite basis vector space, the matrix representation, is no longer needed. Second, only ingredient needed is a definition of the inner product. These self-adjoint operators have some really important properties. We are going to state some of them. First of all its eigenvalues need to be real valued, as in not complex. Recapping our previous notation for the eigenvalue lambda of I with eigenvector v of I, and assuming all eigenvectors to be orthonormal, hence we can state, clearly this is true, or. Now we take the Hermitian conjugate of operator m, hence use the fact that m is self-adjoint, so that, in other words, for lambda of I being an eigenvalue of this self-adjoint operator, it needs to be equal to the complex conjugated value of lambda of I. In other words, it needs to be real. A second important feature. For all self-adjoint operators, eigenvectors with different values for their eigenvalues need to be always orthogonal, as with respect to the inner product. So let's write this out. Voila. We are going to use a similar structured argument as before. But instead of taking the inner product of v of I with itself, we take the inner product of v of I with v of j. Clearly, the statement is true. Going through the mills as before, we take the Hermitian conjugate of m, use the fact that m is self-adjoint, Now we're going to use the properties for the inner product and the fact that v of j is actually an eigenvector of m with eigenvalue lambda of j. Now we use that for all self-adjoint operators, eigenvalues need to be real valued. Rearranging this relationship will result in, clearly, this equation has two solutions. Either lambda of I equals lambda of j, or the inner product of v of I with v of j needs to be 0, proving the above statement. Considering these features of all self-adjoint operators, this has an interesting suggestion lurking in the shadow. Take any self-adjoint operator in vector space V, that its eigenvectors would form a natural choice as basis vector representation of this vector V. Remember, we represented a self-adjoint operator by the letter m and its eigenvectors as v of I, like this. And we already learned that as its eigenvalues, lambda of I is unequal to lambda of j, automatically vector v of I is orthogonal to v of j. A nice vector property to have as for basis vectors. Remember, we defined the self-adjointness of an operator with respect to the inner product of vector spaces in V, not with respect to some representation of V. This is important now. I.e., in this, SA stands for self-adjoint. Or in the bracket notation more common to quantum mechanics, this reads as but, as always, there are some buts to consider. Let's look at them first. What are the buts to be considered? One or more eigenvalues can turn out to be 0. Or what is an identical statement if the determinant of our matrix turns out to be 0. In this case, the dimensions of the space projected on is reduced with respect to the original space. Furthermore, if M is not singular, its invert exists, which turns out to be nice later on. The second but is what to do if eigenvalues turn out to be equal, like this. The set of basis vectors with the same eigenvalues actually span up a subspace in V. And now an extra procedure is needed to make these basis vectors form an orthogonal basis set. In quantum mechanics, this was, for example, to find another Hermitian operator which commutes with the original one and has different eigenvalues in this subspace. But the statement, as it stands, seems sound. Okay, let's go back What was the actual problem we were trying to solve? We studied inhomogeneous differential equations of the form under holonomic boundary conditions. And we read L as a differential operator. Then quite formally, the solution to this inhomogeneous differential equation would read, and the name of the game is to find out an expression for this invert operator L minus 1. This has a sister problem in our finite dimensional linear algebra space. That is solving this equation for a fixed vector of u. But again, we have two restrictions. M needs to be self-adjoint, and we take M to be singular. Then quite formally, the answer reads like this. The sister problem is easier to solve than our actual problem. Let's solve this one first and see what we can learn of the solution, of the structure of the solution for our actual problem. So, we are looking for a practical way to express the solution of u. For this, we take as the orthonormal basis to express all vectors in the eigenvectors of operator M. Operator M being self-adjoint and non-singular. As such, we can expand both vectors u and f as now let's apply M to u, and this would result in using the fact that M is a linear operator, using the fact that v of I is an eigenvector with eigenvalue lambda of I, then solving our original equation would tell us this clearly has one solution. As a result of all this, for vector u we find and we expect the solution of our original problem with the differential operator to have a similar structure. But let's not get ahead of ourselves. Let's play around a bit. What would now happen if we would allow M to be singular? If M is allowed to be singular, either of two things happen. Either this equation has no solution at all, or we have no longer a unique solution. What happens depends on the choice of f.